Uh, Hello everyone. Welcome to this week's Crunch seminar. Today we have one speaker. He's Haokai Wu. He's a PhD candidate in the Department of Civil Engineering at Shanghai Jiao Tong University in China. He earned his master's degree from Tianjin University in 2021 with a major in naval architecture and ocean engineering. His primary research interests include artificial intelligence applications in fluid dynamics, wind engineering, bluff body aerodynamics, and computational fluid dynamics. Hawkeye, thank you so much for joining us today. We know that it's a bit too late, so we're sincerely grateful for your consideration from both you and your advisor, Young. So with this short introduction, you can start whenever you're ready.
I'm ready. And thank you very much for your invitation. And I will start now. And ladies and gentlemen, esteemed professors and dear colleagues, good afternoon. My name is Haokai Wu. I'm a PhD candidate in the Department of Civil Engineering at Shanghai Jiao Tong University. And it's with immense privileges and excitement that I attend the seminar at Brown University to share the fruits of our recent endeavors in the field of AI applications in fluid mechanics. The topic we present today is high flexibility reconstruction of small-scale motions in world turbulence using a generalized zero-shot learning. And this work is guided by my supervisor, Dr. Yong Cao. And my presentation today is divided into 5 parts. Firstly, I will introduce the background and our study motivation to predict the multi-scale world turbulence. And secondly, I will explain the proposed methodology of multi-scale world turbulence reconstruction. And next, I will present the current results of world turbulence reconstruction. And furthermore, I am going to promote our results into practical CFD applications. And finally, we'll get the conclusions. Here, let's begin with the background. As we know, turbulent flows are seen everywhere, including the atmosphere boundary layer, the high Reynolds number wake behind the bluff body. However, in the experiments or field observation, the measurements technique is normally limited. We cannot get the full scales of the turbulence easily. Of course, another tool is numerical simulation, but it requires the high computation cost to obtain high fidelity small-scale edge structures. So we are always pursuing an easy way to predict the small-scale turbulence motions with lower costs. And in the right, another perspective of generating the small-scale turbulent motions is the engineering application of downscaling turbulent boundary layer. For the wind disaster or wind energy estimation, the real-world wind environment is expected by simulating the meteorological models. These models consider the sun, radiation, precipitation, all the wind speed present here, and so on. But we should know that the meteorological models normally have very cost grid relative to the engineering structures. For example, the meteorological models have several kilometers resolution. However, the wind turbine blades, for example, have several meters in size. So when we transfer the turbulent boundary layer flow field from the meteorological models to engineering CFD models, we always suffer the scale gap between two different numerical models. This is another motivation for us to generate small-scale turbulence motions based on a given field. And in traditional CFD applications, we use the multi-scale nesting approach, as shown here, to fill the gap, scale gap mentioned above. But unfortunately, considerable computation costs are required to obtain physically realistic turbulence with sufficiently small scales. Therefore, in the field of multi-scale prediction, a novel approach is highly motivated, which focuses on both precision and efficiency. And in recent decades, data-driven methods have rapidly advanced in deep learning algorithms. It provided efficient solutions for turbulence reconstruction. The left figure shows a typical regression reconstruction model based on supervised learning. The training method is to firstly obtain sparse data through dimensionality reduction, and then establish the mapping relationship between the dimensionality reduction and the whole domain. The results in a previous study show that suitable machine learning methods can realize the rapid prediction of global physical field from sparse measurement data. For this purpose, artificial intelligence gives us a good approach to based on the previous studies for given sparse low resolution input. And here, we hope to propose the model to predict the high resolution turbulent field. Different from the computer vision, we hope our model can meet the physical law and really can be used for CFD simulation and downscaling simulation. And we hope the models had high feasibility of super resolution ratios, and more importantly, they had a high generalization. And so in the second part, we want to talk about the super resolution approach we proposed. In our study, super resolution generative adversarial network, also called GAN, is used as the co-models for low to high resolution construction of water turbulence. And the total loss function of generator in the SR GAN is defined in the lower part of the page. It combines MS loss and adversarial loss and the physics-related loss term to better reconstruct physically realistic turbulence. The result of the continuity question of three-dimensional incompressible flow is selected as the key contribution of the total loss function. And here, lambda 1 and lambda 2 are balanced factors of scale magnitudes. The lambda 1 here is fixed as the 10 to the power of -3 in accordance with the application of Stenger's study here in 2020. And to fully integrate a priori information into the trained model, lambda 2 should be adjusted dynamically such that the combined influence of the physics embedded term constitutes more than 50% of total loss at each training epoch. The proportion 50%.
Okay, I have a question. Here in this case, to compute the derivatives, what are you using? Are you using finite differences or using automatic differentiation?
I use the second order central finite differences scheme.
Oh, okay. I see, I see. And did you try with other, like with more points, or did you find something? Why did you choose this one?
Um, so it's just the first test of my uh difference methods. And
Okay, okay, okay.
and I adjusted the lambda 2 dynamically and to guarantee the terms of the physical related loss contributions uh, constitutes up to 50% of the total loss. And and then the 50% is empirically selected to ensure that waste of the physical related loss contribution are no less than those of the MSE and plus the adversarial loss. This aims to learn the conservation law in fluid fully for the SRGAM model. And this page presents the detailed structure of our SRGAM model, a generator and a discriminator model compete with each other. And from the low resolution inputs, the generator tries to generate the super resolution contributions that approximates the true high resolution flow field. The discriminator D aims to dis dis distinguish the generated and distributions from the true one. The generator G adopts a deep convolutional architecture, which includes 16 consecutive residual connection blocks to elevate the problem of gradient finish during the chaining. Each block contains two parallel convolutional branches and filled with different numbers channels that used to extract features at different levels between two branches. And the activation layer of ReLU is used to introduce the linear mapping. And the extracted features are then upsampled through a subpixel operation and the final convolution layer here to integrate the super resolution flow fields. The discriminator D is employed as a deep convolutional encoder modified from the binary classifier as shown in the right figure. It takes both the reconstructed super resolution flow and high resolution of flow fields as inputs together, and their distribution features are extracted through 8 consecutive downsampling blocks, each consisting of a convolutional layer and a leaky ReLU layer. The last layer employs a fully connective structure to return the probabilities of the inputs distributions being true. Then here we introduce the training data and training method of the SGAM model, also called as a co-models in our proposed method. In terms of the turbulent generation mechanism, channel flow is similar with the boundary layer. Both the channel flow and the boundary layer are influenced by the wall friction. This study also applies the turbulent channel flow database available at Johns Hopkins turbulence databases for only training and validating the performance of GAM model. And the top left figure shows the training and the validation data extractions from a half-page channel domain. The top right figure shows the basic pre-processing and super resolution prediction procedure of turbulent channel flow. The detailed information of training and validation dataset is collected in the table below here. And we use average pooling to obtain the low resolution data to build the data pairs of low resolution inputs and corresponding high resolution labels at a certain dimension difference of n times. And we finally extracted 1,000 snapshots for training and 4,000 snapshots for validating. And in this page, we validate the capability of the 12 times physics-related SR-GAM to reconstruct the super-resolution channel flow fields from 1/12 low-resolution data. The instantaneous super-resolution field of one normal velocity component is compared with the DNS snapshot at the same instant. And the physics embedded SR-GAM model could successfully generate the velocity fluctuation at small scales that are seriously missing in a low-resolution input near the wall. The effects of the embedded physical loss terms on the SR-GAM training process is further assessed in the second law. A subdomain is extracted in the wall for detailed comparison. With the help of embedded loss of the continuity, the lowering patterns of the flow structures are reproduced better. And to further reflect the impact of physical loss terms, the mean absolute divergence, also called MAD, it reflects the residuals of the continuity equation, and here we will evaluate in the right figures. The MAD is obtained by average over time and over the space at the same height. Smaller MAD values approaching 0 indicates a close match between reconstructed and the true incompressible flow fields. When the residuals of the continuity equation are embedded, MAD decreases by 2 or 3 times in corresponding height below the low log region. In the next step, the core model and the SR-GAM model trained by the turbulence channel flow is directly applied to super resolution reconstruction of turbulent boundary layer without using the additional data samples in the boundary layer dataset for model fine-tuning. This model application approach can also be called as a zero-shot transfer. In practice, the turbulent data is to be predicted often have limited resolution and insufficient high fidelity samples. So the embodiment of the zero-shot transfer capability is the strong proof of the strong applicability of the reconstruction model. There are also some noteworthy points about the testing of turbulent boundary layer reconstruction. The testing set is constituted by the velocity fields from only one target YZ closed plane. The turbulence was verified to be fully developed. The low resolution input was obtained by reducing the size of high resolution labeled by n times, which was realized by average pooling plus the Gaussian low plus filtering together. This mimics the energy dissipation of small scale flow structure when the turbulent boundary layer simulation is conducted in a low resolution grids. And without any transfer training, the physics embedded SR-GAM model is directly utilized to predict the super resolution velocity fields of turbulent boundary layer. And here, the 5 times super resolution of the turbulent boundary layer is taken as the first testing case. And from the instantaneous reconstruction results, the super resolution field shows severe magnitude underestimations and no physical fluctuations here compared with the DNS truth. And from the corresponding wave number spectral results, the SR models fail to recover the velocity intensity of DNS results at larger scales and violating the -5 third power law in the inertial subregion. The spectrum rebounded at the approximately the cutoff wave number of the low resolution. And it accounts for the old fluctuations in instantaneous fields. The observation reflects the zero shock transfer, relying only a SR model cannot generate the physically realistic turbulence.
Oh, okay. Another question. Maybe you mentioned already. What was the Reynolds numbers for this problem?
You can act. Okay.
What was the Reynolds number for this problem, or the Rayleigh number, or
No,
This is the boundary layer.
it's about the rate.
It doesn't know
It's
this is the
about
anything.
boundary?
He doesn't know anything about fluid. The Reynolds
What did
number
you
is
say, Ahmad? Ahmad, sorry, you were saying something?
That's just the real number of turbulent boundary layer.
Okay,
Oh,
so it's
it's the
1300.
it's based on the RE tau, because if you base it on X, it changes from the beginning to the end. So it's better to report it as RE tau, which is the correct way to report here.
Yeah, that was what I
okay.
was asking. What was the terrible the Reynolds number?
Oh yeah.
So it's 1300, right?
Yeah, I have a
It's,
question here also.
mm,
So 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 maybe you later show that. So do you have a case that you have performed a low resolution turbulence CFD and then use that to generate ground truth and compare it with the DNS? I mean, you don't use DNS and filter it down and then use it. So in actual case, right, you run a CFD test case using a very coarse resolution, right? And then can you use your method to generate small scales from that and then compare that with a DNS results of the same case? Would that work?
so it can work and present later.
Oh, yeah, okay, perfect, thanks.
And, and here is this is the first initial test of the only salt SR gum to reconstruct the turbulent boundary layer. It's our initial test. Mm. And here, and let's go on. And so we see the drawbacks of the only a SR gum cannot generate the physically realistic turbulence here. And so we design here a new framework to solve the above drawbacks. We built our new framework based on the energy cascade theory of the turbulence. The theory says in turbulence flows, energy is injected into the system at large scales. The integral scales are the scales of the largest eddies of the flow, and the energy then transferred down from one scale to another, progressively moving from larger eddies to smaller ones, and these smaller eddies further break down into even smaller eddies, where we call Taylor scale. And in a certain range of Taylor scale, the smaller scale flows act similarly with their larger counterparts in structure and dynamics. And it obeys the well-known minor 5/3 power law in energy spectrum within this range of scales, as shown by the figure. And this energy transfer process will continue until the energy reaches the smaller scales where it eventually dissipated. And Kolmogorov scale is defined in the dissipation range. And another noteworthy point is that the Tyler scale is about 1/6 of the integral scale, and this relationship will be used in our new framework. And this page, I will show the schematics workflow of the energy cascade SR-GAM. We also call it ECSR-GAM framework. We employ it in our reconstructing multi-scale turbulent boundary layer. And in order to gradually recover the wall turbulence energy from large to small scale, two or multiple resolution iterations are required for the low resolution filtering input in ECSR-GAM framework. And in each iteration, the chain SR-GAM model is used as the code of upsampling to enhance the grid resolution of turbulence. Before upsampling, the downsampling model is added here to filter out the flow components that dissipate too much energy from the low resolution input. In these first procedures, we calculate the integral scale first and compare it with the cutoff scale of the low resolution input to determine the coefficient R of downsampling. The downsampling model is actually a bicubic interpolation and is used to further downsample the low resolution fields to sparser grid distributions where the minimum scale will be nearly the integral scale. This step provides a new opportunity for super resolution processing to accurately reproduce the large scale structure of the flow fields. Once the energy recovery is achieved on a large scale, it's expected that the flow field structure at smaller scale can be gradually inferred through the energy cascade theory we mentioned about. And in the second of the super resolution procedures, the initially reconstructed fields here are downsampled by another interpolation or the downsample model with the ratio of 1/6. And the ratio is determined based on the approximations. The Taylor scale is typically about 1/6 of the integral scale for high Reynolds number turbulence. And then we use the downsampled fields, and downsampled fields are reconstructed once more by the SR-GAM model to infer the smaller flow structures. And the iteration should be reconducted until two conditions are both satisfied. Here, firstly, the reconstructed flow fields exceeds the target resolution of the high resolution ones, and secondly, for the super resolution outputs, the cutoff wave number of the initial subregion is larger than 6 times of the wave number corresponding to the integral length. And as the final process, super resolution outputs are required to align with the target resolution, so the final downsampling ratio could be determined. This is the whole workflow of our ECSR-GAM framework. And next section, we will focus on the applicability of zero-shot reconstruction using our SR-GAN framework. A super-resolution code is inserted into ACSR-GAN framework to enforce n times reconstruction. And here, at first, we enforce the 5 times reconstruction here. The figures show the instantaneous turbulent boundary layer of 3 velocity components of DNAs. The field low resolution input here. And through the first super resolution procedure, the reconstructed patterns of large scale velocity structure matched well with those of the DNA sphere. And the second super resolution procedure is hence required in order to further recover the turbulent energies within the large scale wave number range and reproduce the smaller scale velocity fluctuations. And in these figures, the smaller scale structures near the wall could be generated more fully through the second super resolution procedure, in despite of slight underestimations in velocity magnitudes. And next, we show the horizontal wave number spectra of 3 velocity components. Here we represent the U components at first. Here, during the first reconstruction procedures, the turbulence energy recovered towards that of DNS results. The -5/3 downward chance persists up to 2 to 4 times of the wave number, corresponding to the integral length scale of the low resolution inputs. And then the dissipation occurs as the wave number becomes higher, as indicated by the brown lines. And after the second reconstruction procedure, the predicted inertial subrange are further extended to more than 10 times of the wave number corresponding to the integral scale, with further energy recovery at larger scales and the small scale together, indicated by the purple lines. And
sorry, I have a question here. So for about the procedure 1, you can see the large scale spectrum is better, right? So what kind of information you are using here to train the model?
Information.
Yeah, what kind of data? Do you use the spectrum itself or use the real DNS data?
It's all changed by the channel flow, and I'll show in the first procedure is we use the n times SR-GAN here, and the n times here is the same as the n times GAN models in the second procedure. It's the same, and the SR-GAN models are both changed by the channel flow.
So finally, you are using the DNS data as your data, right? So the DNS is instantaneous data, instantaneous velocity field as your data, right?
Yes, DNS instantaneous data of the channel flow.
Okay,
Yeah.
I see. Thank you.
And here, and we present two another components, EVV and spectrum WW, and the other two components act similarly with that in the string-wise velocity And these energy expansions signified that through a minimum of 2 reconstruction steps or procedures, the small-scale velocity characteristics could be physically preserved from high-fidelity turbulent boundary layer fields. And furthermore, we expect that our ECSR GAM framework could realize the turbulent boundary layer reconstruction with multiple super resolution ratios from different level of coarse turbulence fields. It is the key point to guarantee the feasibility of ECSR GAM. The left figures present the instantaneous fields reconstructed by our framework from 1/7 and to 1/7 and 1/12 low resolution inputs. And the ECSR GAM framework could maintain similar reconstruction performances, even though it is input by low resolution field with different filtering levels. And the right figure here shows the wave number spectrum of the world normal velocity fields reconstructed from different levels of low resolution inputs. And despite slight energy loss here, the framework succeed in replicating the minor 5/3 law of energy cascade in the inertial subrange, irrespective of the low resolution levels provided. Yes. So we can say the proposed framework shows commendable robustness in turbulent boundary layers reconstruction against the mesh costness of the low resolution fields. And at last, we verify the generalization capability of ECSR GAM framework across different data sets. Beside the data from John Hopkinson turbulent boundary database with Reynolds number of around 1,300, another turbulent boundary layer with even higher Reynolds number is selected for a reconstruction testing from points dataset. The dataset is another DNS dataset collecting in the University of Michigan. And for 7 times the resolution of the ECSR GAM, we compare the reconstruction performances between different turbulent boundary layer datasets in the left table. The performances are evaluated by R² and MLD, we mentioned before, where the MLD computer closed shear domain dominating regions reflects the reproducibility of the incompressible flow between the different data sets. Our framework can both achieve good fitting of velocity fluctuation. It is indicated by the high R² values, and they maintain similar physical fidelity reflected by the similar MAD value. The right figure shows the wave number spectra of 3 reconstructed velocity component fields. Velocity data with higher Reynolds number, energy cascade in the inertial subrange can still be well reproduced.
Sorry, I have a question here. How did you generate 1/7 LR input?
The next is the same with the 1/5 is the first average pooling, and then the Gaussian low pass field to get the
this is a filter of the DNS simulation. This is a
No, it's just the we use the first to filter the energies on at the smaller scales. It's just a uh, how to say, just the
this is
initial test filter to mimic the turbulence in a coarser grid.
but you generated that using the DNS data, right? You filtered the DNS data and then you input it as
Yes,
a core
that's right.
resolution. Okay. Okay. Thank you.
Yes, and here we were also considering the reason why the current framework shows remarkable generalization capability across different turbulent boundary layer data sets. And it's e essential that the turbulence contains similarities in vertex structures across a spectrum of spatial scales. And fortunately, the convolutional filters in our SRGAM model burden the task to compress and expand the multi-scale distributions of turbulence fields. And they plays a significant role in nonlinearly capturing the data features linked to the invariance of the velocity gradient tensors. Uh, Therefore, across different the turbulent boundary layer data sets, the similarities of the multi-scale but vertical structures could be well preserved. And in the last section, we conclude the results of multi-scale turbulent boundary layer reconstruction using our ECS framework. And in the following section, we want to introduce some applications of super resolution turbulent boundary layer fields to CFD. And specifically, the general CFD uses nesting methods to downscale the flow field, which brings a large calculation cost. Fortunately, we've got the ECSR here, and we can directly use our framework as an interface to realize the rapid downscaling of flow fields at the inflow region here. And we apply the downscaling flow as input, and then expect to simulate a smaller scale field at a much lower and a much quick calculation. Yes. And besides the spatial resolution, we also enforce the temporal refinements for turbulent boundary layer data before inputting it into the CFD domain of finer grids. According to basic flow reconstruction approach of Kami, we firstly enforce spatial super resolution by ECSR GAM framework, and secondly generate another SR model to realize temporal super resolution. And the training data set of temporal model is present here in the left table. It also comes from the channel flow data set of Johns Hopkins turbulent database. And after trained by channel flow, the model is directly transferred to the temporal super resolution of turbulent boundary layer. Here we take the 5 times super resolution as an example. We verify the performance of the temporal model at a location and in shear dominating region. As shown by the bottom right figure here, the wave number spectrums of super resolution data match well with that of DNS choose, and from the field low resolution input. And here we present the computation domain and the boundary conditions of our inflows test of our reconstructed turbulent boundary layer. The input data are super resolution, time-varying velocity. In the table below, the turbulent boundary layer parameters before and after reconstructions are present. And we plan to realize 10 times spatial super resolution and 5 times temporal super resolution. And in this page, we respectively use low resolution and super resolution data as inflow condition to examine the multi-scale characteristics of stimulate turbulent boundary layer fields. The closed plane X to L equals 15 is selected to analyze the simulation performance of different inflows. And L here is the width of the inflow plane. And the figures shows the instantaneous velocity fields of low resolution inflows and the super resolution inflows. And it shows that instantaneous velocity fields of the low resolution inflows have significant lower magnitude compared with those of high resolution inflow. And in addition to the intensity, the recovery of the large scale vertex structures, the instantaneous flow field of the super resolution inflow contains more obvious small scale structures and the stronger structures, and which is closer to the results of the high resolution inflows. And next, we shows the horizontal with number spectra of the 3 velocity components at different distance from the inflow region. Compared with the low resolution inflow, the wave number spectra of the super resolution inflow match better with the DNS inflows here in magnitudes, especially in inertial subrange. According to different distance from the inflow region. And in the streamwise direction, this page focused on the arrow race of turbulent kinetic energy when low resolution and super resolution inflows are input together, are input to compare with each other. And the arrow rays are computed by comparing the results of DNS inflows and other inflows. As the distance from the inflows plane increases, the arrow rays of the turbulent kinetic energy becomes slightly lower. However, it's still obviously higher than those of super resolution inflows. When the super resolution ratio becomes larger from 5 to 10, the differences of error rates are more significant, while the error rates of the super resolution inflows remains relatively stable. And this illustrates the robustness of the current downscaling method based on super resolution models or super resolution frames or frameworks. And now that let's summarize what we've achieved so far. In order to bridge the scale gap between the traditional meteorological models and CFD models, and overcome the limitations of existing AI models, we proposed the ECSR-GAN, a flexible framework designed to reconstruct the small-scale motions in world turbulence through zero-shot transfer. And the results of the current study can be summarized in the following 3 conclusions. And first, the framework shows remarkable transfer capability by accurately predicting the instantaneous velocity fields of turbulent boundary layer and reproducing with numbered spectra with high fidelity compared to DNS results. And the framework secondly, the framework shows the high flexibility in reconstruction from various levels of cost flow fields while preserving physical accuracy. And last, and our framework has a high robustness in turbulent boundary layer reconstruction across different data sets. It's likely due to its incorporation of scale invariance in turbulence. And our findings and the results are collected and published in Journal of Fluid Mechanics Rapids this year, a few months ago. And here is our study team, Dr. Yong Cao, the leader of our team, and he's my supervisor and dedicated to research of AI for fluid mechanics and wind engineering energy, and me, Haokai Wu, and advancing study the AI too, AI on the wind engineering too. And special thanks will also be given to some experts who supported our study, including academician Gui Li, Professor Wenli Chen, and in Harbin Institute of Technology. And we're also grateful to Professor Dai Zhou, Zhao Ronghan, and Kai Zhang in Shanghai Jiao Tong University for their help. And that's all. Thank you for your attention, and criticism and correction are welcome. Thank you very much.
Great. Thank you so much, Haokai, for this wonderful presentation. Do you have any questions from the audience?
Yep. Hi. Hi,
Yes.
Haokai. Great talk.
Go
I'm
ahead.
Vivek. I'm a PhD student working with Professor George Karnidakis. Great talk. I have a question. So can you go to one of the slides where you showed the boundary layer across X, Y, and Z in the 3D section?
But fine. I'm looking for the slide. Maybe former.
Yeah, that is good. Yeah. So my question is, so after you do the super resolution, if you consider the super result or the output of the SR gun at, say, 2 slices along the X direction that are close to each other, is there a continuity across the smaller scales?
Well, I think it's a continuity. We show the two
Across x-axis.
okay, just two planes. Two planes. We only calculate. We calculate the risks of the continuity questions of incompressible 3D flow. Here we extract the two consecutive two planes to calculate the mixture here.
Right. Okay. Okay. You have the physics embedding term, which is across all the 3 axes. Okay. Understood. Yeah. Maybe
Yes,
you could. Yeah. Thank you. Thank you. Great talk. Thank you.
Thank you. Thank you.
Great. Do we have any other questions?
Yes, I have one question. Hi, Haokai. I'm Siavash. I'm a postdoc in applied maths at Brown University. So for the final results that you showed, did you also characterize the errors in the velocity itself? Maybe I missed it. So I know you showed the spectrum and they were matching perfectly, but did you also compare, like, what is the maximum error in velocities in U, V, and W?
Final results. Slide. Is this?
Yes, like one of these results.
Yes, it's the results of the inflow test of S, and our super resolution output is as the influence conditions of the test. And here we found the UVW. Here is our first attempt to examine our super resolution outputs. And whether it could adapt to the CFD applications. So we do the first initial examinations to examine the ability of the downscaling methods, and we just present the quality comparison here, and the tail quantity error compare will be conducting our further study, and it's a great suggestion from you. Thank you.
Okay, got it. Thank you.
I also have a question. I'm a postdoc here at Brown University. So if I understand correctly, you are going to use this method to provide some inflow conditions of your for example DNS or areas simulation, right? Based on some coarse simulation, right?
Yes.
If you provide this model as time series of coarse results, so there will be not only the spectral over space, also a spectral over time, right? Frequency. So have you ever considered the the spectral over time of your output? I mean the output of this SR GAN model. So that is also important in your physical, in your, for example, DNS calculation, because you need the correct time frequency and the time spectrum as a part of the inlet conditions.
Yes, it's our final plan is to do the spatial and the temporal resolution together, and
yes,
they will make the two steps, and first the spatial and secondly the temporal models to examine the temporal and the spatial velocity spectra here.
Yes, I think just as Vivek asked, so because we are also doing something similar, so from some course data to get the high resolution result, but this process is somehow random, because when you want to get some small scale structure from the large scale, it depends on your model, right? But these small scales also matters a long time. So if you use several, separated or independent input a long time, and get of course you can get small scales in space, and maybe the spectral along space is correct, but the spectral along time, they are related, they are not independent, right? In physics. So I think maybe we should also consider in that correlation along time, if you want to use that as a inlet boundary condition of your areas or DNS simulation.
So creations is very important thing. Just as you said, and we are doing the temporal and the spatial super resolutions right now, and considering how to combine it better in our studies. So we are trying to do the better models to
So thank you.
realize it.
Great talk.
Great. Thank you so much for your questions. Do you have any other questions? If not, I think that we can close this week's seminar. Haokai, again, thank you so much for staying up late, and thank you so much for your time today. This was a really nice talk. Yeah, I think that you will receive an email in a next day, then, because Nasani usually uploads this link to YouTube, so then you can share it in your social media. Okay, great.
Thank you.
Thank you,
very
everyone.
much.
Thank you, everyone, for your time, and I hope you have a nice week. See you next week.
So, goodbye.